Now we will go back and we will see what the math is. Simple, it is only representation, we are not even looking at the math in detail, it is only a representation. Okay. Similar to the problem that what we have seen, I want to get Wt psi, I am making this a generic approximation, I want to identify f hat. What is this psi? The psi is a basis function, in our case it is the radial basis function. What is this x? This x is the sampling points, meaning the new points where I seek the function value. I am just making a generic formulation here. Okay. So, this x could be anything that you want, okay, wherever, whichever point that you want. What is the c? C is the center of the ith basis function. So, in the example that we discussed, there were 3 basis functions that we used, 3 triangles, and this c I, since I am calling it I in the superscript, is the center of the ith basis function. Okay. And you also please remember that we are doing a sum here. Okay. So, if your x so if your x was in the right of the third function, then I will look for C3, that is what it means. Okay. So, I will look for C3. Yeah. So, this is a psi is going to take some shape, we will see what shapes are possible, but this is nothing but your x. Okay. So, this is like this psi is an equivalent of your slope in our y equals mx plus c. So, you cannot directly compare, but for you to relate I am giving this. Okay. Do not record this. Okay. This is for you to relate immediately. Okay. You give me any new x, okay, with the same m, I will be able to find the new y for you. Okay. But as my m changes, what is going to change? The line is going to change. So is the case here. Okay. The psi tells me the m part of it in one, not the m part of it, but mx plus c kind of stuff. Okay. Mx is what this guy is about, and then this x is nothing but this one. So, I am just giving the x in a relative sense. Imagine that this x is not directly x, but you normalize this x and give. Okay. So, if I am saying x is 120, you can feed it as 20 because your normalized version is 100 is equal to 0, that is all. This is in a normalized sense, that is it. Okay. Now, there are two things, you need to find your w, that is one thing, which can be done using a simple maximum likelihood kind of an estimate. Okay. So, we will see what are the forms that this psi can take, what are the forms that we have already been exposed to through the examples, and then we saw something like this, correct, or I mean it was, yeah, nice fat. These are the two forms, but there are also different forms that are, they are all governed by some equation. Okay. Psi of r, r is just the difference, normalized sense, let us say it is linear, the one that we discussed. Okay. It could be cubic, r cube. So, for every distance, for 1 it will be 1, for 2 it will be 8. Okay. Then there is something called a thin plate cubic. So, it goes in this form, r squared times log of r. There is some multiquadric. Something that we are interested in general is our Gaussian. So, the Gaussian, if you see, is slightly different from the top. The top requires only one parameter, but you know with one parameter I have only some control. 2 parameters I am likely to have better control. Okay. I can control the shape as well as the size. In this I can only control the shape. If you look at it in the first one, r cube, r squared, I can only control the shape, whereas in the second one I can also contain the size. Okay. That is the advantage of doing, but you will have to find this guy, that is another there is another, you are introducing another parameter, trying to get more control, you are trying to introduce another parameter. Okay. It is basically features. Okay. If you want to do more, you need more features on your cell phone. Okay. A basic phone, yes, you can get it for how many rupees, man, 1000 rupees you can get a Samsung Nokia 105, but it will let you only call and receive calls, okay. But you want to do internet, you want to have Google Maps, you want to go elsewhere, you want to do WhatsApp, you want more features, then you need to pay more. That is what the idea is. You need to pay more in terms of computational sense, okay. Okay. So, these are the stuff that we have already discussed. Generally, RBFs increase or decrease monotonically from the center. The beauty of RBF or any of the approximation that we are talking about is, however complex your expressions are, you are still doing only a linear superposition. You are only going to solve for these W's in a linear regression sense. It is not a nonlinear, but the psi could be the most complex. Okay. Sometimes I do not even remember the error functions that are built, I just choose Gaussian, okay. But it is still, from a solution sense, it is still only a linear regression, because you remember the Gramian matrix that we discussed about, right, x transpose x inverse, that is what you are going to do. That will still remain the same, that nothing will change, because that is only a function of your x, the Gram matrix is only that part, okay, that is not going to change. So, that is the beauty of all these guys, okay. But anyway, the question is, that is great, but what is the psi that I will choose, because you do not have the original function. Just like I showed you in the example, the original function could have been anything. How do I know? Okay, this is the challenge. Whenever we go, you know, even with industry practitioners we go, people generally ask, how many design of experiment points should I use? No one knows. If I know that, then I will copyright that and I will be one of the richest profs, or at least in that community I will become one of the richest person, because invariably anyone who is trying to do design using computer models today will use a design of experiment. And there is a very underlying question is, how many points should I use for these many dimensions? There is no thumb rule at all. That is when the designer comes into picture. You need to have some understanding of what the problem is, okay. I know that this is a complex cantilever problem, but you think still it will only give you a cantilever kind of an effect, then it is going to vary only in terms of L cube. What is maximum it will vary? Maybe 3.5, not cubic, it is 3.5, good enough. I will use a fourth order equation, at least that the engineer should be able to feed in, because depending on the order of the equation, my number of coefficients that I need to find is going to vary, for which the number of data that I want are more, accordingly I need to do that, okay. Then always you have a computational budget. The computational budget will let you only find 2 unknowns, but you are prescribing a fourth order polynomial. I cannot do that. So, then what I need to do is I need to find a balance. Can I fit something that I know is not accurate, but at least will give me an idea on how far I am from the original predictions. So, then I will make those decisions, okay. This is what people have been able to do. So, the whole idea right now that we spoke about is the data. This is parallel to the question that you asked, okay. The data is not noisy, the data is kind of a deterministic data, which is, so the one thing that you need to appreciate is these ideas come out of days, which is design and analysis of computer experiments. So, computer experiments, there is no noise, you give the input, it will give you the same output, okay, any MATLAB code, anything, okay. So, you give a wrong output, it will give a wrong input, it will give a wrong output, but that is fine, but the wrong output will be consistent every time, unless you have a random number generator inside which does something for you, okay. If it is an analysis stuff, it is only deterministic in sense. So, the assumption that so far we discussed is, there is no noise in the data per se, but that is not true in experimental sense. Does it mean that RBF can only be used for applications like a computer simulation? No, that is not true. You can use it for any kind of a function approximation, which is what makes it meaningful and sensible, right. So, the question is, what happens if the data is noisy? Then what it means is, you do not expect the curve to go through all the points, okay. Unless you have 100% confidence on the data you have, you do not want that, because you know that it also has errors, correct. The points that you estimated also might have errors. Then you want to do only an average sense. See, you remember, please remember the stress strain curve that I told you in the beginning. Whatever you got in the book is a lie. They did not tell you exactly how they got this, okay, it was actually like this. And then why didn't I go through the points? I only averaged it, because if I went and did it in a different machine, I might get a slightly bigger or a smaller spectrum. Okay, I change the guy who tightened the specimen, I might get a slightly different one. Okay, even my Young's modulus might change accordingly little bit. The material, the moment I put the second specimen, I might get a slightly different result. Okay, so the curves that you see are average curves, which is not explicitly mentioned. So you don't want to follow any of these lines, because these data themselves are noisy. See, anything that you see, in one sense that is also good. Any electrical signal that you see has noise. One thing that is related to your life is what? Your ECG signal. Have you seen your ECG signals or anyone's ECG signal? Okay, this signal has noise, but it also captures your PQRST, which is in your the lub-dub of your heart, right? But that should be very clear like this. It is very clear, lub-dub, and there is a small, so it is PQRST, that is what. But then the signal is always like this. You put a strain gauge and get some strain signals, it is always like this. So it is corrupted with noise. Okay, noise means not the noise that we know as noise. Okay, it could be electrical noise, it could be your fitting, the way in which you have fastened it and all that. What happens if there is no noise, especially in your electrical signal? The story is over. Okay, so there is always scope when there is noise for improvement and for betterment. Okay, so this is why I like optimization and data fitting in general, because they are very reflective of your life. If you do not get some results, okay, you should not crib about it, rather you should look at this as an opportunity, because if you say, if you get your results, then the job stops there. Okay, there is no further scope in research. Okay, but don't look for not getting results, you should get results, but if you do not get results, do not worry about it. Okay, so non-linearities offer you opportunities to improve and grow. So then what people do in such cases is, if the data is noisy, then you do not want the data, the fitted model to pass through all the points, not necessarily. Okay, I want only an average fit. In that case, we use something called a regularization parameter. This is more like what do you call, like trying to preserve the pattern, I am trying to preserve the topography kind of an idea. Okay, so it is this is widely used in machine learning techniques, these regularization schemes. Okay, so this is just your identity matrix. The phi is nothing but the matrix of your basis functions, and depending on your ideally this lambda, what you are trying to do is you are trying to take your basis functions and you are trying to add the noise to it. Ideally what should be your lambda then? It should be the noise. Okay, but you do not know the noise. If you know the noise, you would to begin with itself you will do a better job. Okay, you do not know the noise. So ideally the lambda should be equal to the noise in the data. You get the point or not? Okay, so usually it should be the noise in the data, but we do not know it, hence it is introducing another parameter. Then what happens, people will try to tune the lambda. So you are introducing a third parameter. Okay, from whatever we discussed so far. Okay, from whatever we have discussed so far, you introduce a new parameter, which is the regularization parameter. So you will have to choose a regularization parameter in such a way your error metric will go to minimum. That is all the overall idea is, right? In our least square also, what did you try to do? I am fitting and I am trying to compare it with my original realizations, and you please appreciate the point that even in the polynomial regression it does not go through all the points, it is only the best fit. The question is, how do you define what your best fit? Your best fit was not that the point should go through all the points, my overall error should be minimal. So that criteria will still remain the same. In this what you will do is along with your the basis function parameters, you will also tune your lambda such that your overall error is going to be less. So that does not necessarily mean that your curve should pass through the points that you have, because the points themselves might have errors. So forcing them to go through that means that it will still be erroneous. So you do not want to do it. Okay. So, that is one way to deal with noisy data. Okay, most of these curves are taken out of the internet, and the Forrester's book has enough examples for you to study. So, there are different types of radial basis functions that I exposed to you, at least from a picture perspective. We looked at the equations, right. So, there is a linear variation, there is a cubic, there is a thin plate cube, there is a multiquadric, there is an inverse multiquadric, meaning 1 over this guy, and then the Gaussian function. There could be other types of functions as well. Okay. So, we saw all these things. For instance, just to give you an idea in a Gaussian sense. So, let us say that the pink dots that you see are the bunch of data that I had, and I wanted to approximate that function. So, what we are using here is we are using 1, 2, 3, 4, 5 radial basis functions. Okay. So, we are taking them and then we are getting this kind of an approximation, and when I add them up, this is simple. If you see here, up to here, you can see how this linear superposition works, right. Up to here it is the same guy, there is nothing. So, the function, the approximated function just follows the blue curve, but from here I also add the green curve and the red curve's value. Okay. So, then you can see there is a small deviation from the blue curve. When it goes here, the blue is peak, but I also get some value from here and I get some value from here. So, those two added up and it gets fitted like this. Okay. This is one of the best fittings. Okay. But the reason is there are also a lot of points you can see, and the line does not pass through all the points. So, this is an average fitting in that sense. Kiran. Those are one RBF. They will correspond to the 400 kind of stuff. For instance, this guy is at 400 kind of stuff. Sorry? Mm-hmm. They will not. Why should they? So, this is basically, it is also capturing your what you call your variations and your mu value, because at this point, see, okay, I see what your question is. If my functions were like this, I will just take the same example. Okay, I see what your question is. If my function, okay, I see your question, just hold on. If my functions were like this, then it should pass through that, correct, because at this point, though I am going to say RBF1, RBF2, RBF3, RBF3 is only going to play a role, but in this case what is happening is, so at this point I am going to add all the 3 blues. So, there are contribution from the other RBFs also. So, because if you see the fitted line, I guess that you will agree, right, because this is my mu value and this is the value from the green value, this is from the blue, this is from the other blue, all put together I will be able to go here. I am building upon the scaffolds that each one gives me. Okay. So, that is why the same reason that you pointed out. In the other example, we had 3 points, but then they ended and then only the next one started. But here it is not like that, it started it going and then this guy is also starting here and coming like this. So, it will add up like that. You get the point? So, this is basically with the regularization parameter. Yeah, tell me. Sorry? The basis function? Sigma are the same. Sigmas are the same. Sigma means how fat they are. At least visually from this you can say that the sigmas are the same for all of them. They are all equally fat. Okay. Height wise they are different. That is all. And the form is the same. The form is the same. The parameter that varies is only your mu. So, where does this dwarf and the heights come into picture? Remember this example, where did they come? There was one more stuff. This is just the psi that you are talking about. The fatness is a function, I mean the fatness is one thing, okay, and then I did something like this. So, this is just, let us not worry about this, this is just the new point prediction, right, and the psi is located around some xi's. There was one more thing in this example, what was that? Lambda was for the regularization. Okay. So, the weights, I am going to say I will give more weight for this guy because he is located around this point and there is only one of this guy, whereas for this guy I will give a slightly lesser weight, for this guy maybe equal weight, but that weight will come out of your regression. Right now we have seen only the interpolation part, you understand, right. So, I was under the assumption that the regression part is understood, I did not explicitly say that. This gives you the idea about the interpolation. But his question is, how did you decide that the green is only this tall and the red is this tall? That comes from the fact that you will have to estimate your WIs. Your WIs are nothing but your weights or the coefficients of each of these guys. So, you are giving more weight for this guy, you are giving less weight for that. Actually speaking, all of these guys are like this bus, all of them are that one value to begin with, okay. Then with respect to these points, you are going to take a sum of them. You are going to solve that. This is what you are going to solve, W transpose psi. To begin with, what you will do is the psi is the same for all of them, okay, meaning sorry, the weights are the same for all of them, psi is anyways the same, psi I is the same, the only thing that will differ is your the center, okay, it is actually xi minus c, only the center will vary. To begin with, you will just have all of them like this, let us say. I have 4 radial basis function, all of them will be the same to begin with. Same means only the centers will be different. Of course, the how fat they are also is fixed, the weights. I am using the same weights for all of them. Then what I will do, here are the data points that I have, something like this I will say. Then based on the metric that I choose, I will have to find out what my W's are. What this W will say is leave it like this. For this particular stuff, the first one, just leave your weight at that point, it will say. Then for the second one, it will say probably you need to increase a little bit more. So, the new I do not know, this yellow might not be a good. For this one, it might say let us go up a little bit so that you can capture this peak. And then for this one, it might say do not go that far, just go this much, it is enough. So, what it means is the height will be adjusted based on your W, or your W is corresponds to your height, that is what it is, okay. So, that is just a regression problem. So, this is what radial basis is about, then that becomes a just a regression problem, that is all, okay. Any question? Sorry? How do you choose? Oh, for the Gaussian distribution, I am sure there are ways to fit that, and but that is also a parameter. That is what I told, you know, like, yeah, that is also a parameter that you might want to tune. But the point in that is, but it is fixed for all of them, okay. But in Kriging, what happens is it, yeah, it can change for each one of them. That is the difference between Kriging and this one, okay. So, the mu also you can vary, but it's, you know, it's one less computation if you put your mu to be at the center, okay. These are different such examples. For instance, in this particular case, this is the actual line that they wanted to approximate. So, as you can see, there are too many of these guys, it is not varying, right. So, all of them are of the same height, you add them up, you will get this guy, and then at this point I am using multiple set stuff, okay. And people have done, so this is just 1D so far we saw. 2D, there are also these kind of different functions are available. This is how a bivariate Gaussian would look like. I do not know, this is a quadric probably, and this is quadric, this is inverse quadric probably. Quadric means you understand, right? Quadratic is 2, quadric is 4 kind of. Okay. So, 3D how can I do? So, multiple Gaussians, these are the different centers. This is one center, this is one center, this is one center, okay, and then I can add them up. So, what I might get is, I might get a function in space. You understand, right? So, at this point it is going to add up this value and this value, or I could have another function also here, another Gaussian function I could have, then it will get added up. One example that I give people is, imagine that there are people sitting in this room and then I throw a bedspread on you. Not all of you are of the same height, okay. So, he is taller, he is shorter, she is shorter, she is taller, okay. So, when I put a bedspread on all of you, it is going to go like this and come, okay. Now, randomly I took 10 people out of the 30 people who are sitting here, randomly. I do not have a bias, I am not taking only these people, I randomly did. What will happen? It will dip further, okay, and it might go a little more on that side and it might dip further, depending on how there are 2 people who are taller and taller on that side, then the function will go up like that, okay. So, if I were to approximate the function, imagine that I can just approximate your head, this side and this side, I can approximate your head, basically the curvature is what I am trying to do, okay. And I just take the height of you and then I take the curvature, that is one thing. I add that up to the second guy, I add that to the third guy, I add that to the nth guy, then I can approximate how the bedspread looks like, linear superposition. I am just going to add each one of you and it might become an overfit, because that is what was the actual one, but then I remove 10 people. So, what happens is there is an artifact, there is a sudden dip and then it goes up, but that was not the original function. Just because I pull this person from there, it went like that. Pulling this person is equivalent to not having the data point, but now when you fit, what you will fit? You will fit it like this, that becomes an overfit, but you do not know that it is an overfit because you do not know the original function. So, that, I mean, there are no ways to eliminate that, but you can address that, okay. So, this example tells you that it is not enough if you look at it only from a output response perspective, you also have to look it up from an input response perspective, okay. You had 25 people here and you had only 5 people in this, okay, and then you are approximating the function as a whole of 25 people. That is not okay, because in this side of the column there were only 5 people as against 10 people in each of these columns, okay. So, here it is sparse representation of this column compared to these 2 people. So, your output should record that value with respect to your x's. Currently we do not, radial basis in one sense does, but still it is centered. It says in my neighborhood how much does it vary, and it does really not capture that, though it is an Euclidean distance and all that, it does not really capture it fully, okay. So, Kriging introduces a little bit more information into that, we will see how it does that, okay. Just to give you an idea in 3D how this one works, not 3D, this is still 2D, okay, for Kriging, for radial basis idea. So, x, y and z, okay. So, we are looking at x, y as input and let us say z as the output. These are the 3 surfaces that I have fitted, okay. So, this is a classical example like the way that I told you, right, for the triangular first linearly varying problem. I said, like, imagine that your basis functions, each basis function extends across your design domain, that is the case here. So, it is not stopping anywhere, it is going across your design domain, each one of them, okay. So, this is centered at some other point, the red is centered at some other point, the green is centered at some other point, okay, but all of them are running across your design domain, okay. So, now imagine that I am using a cutting plane here, okay. Then the visualization from x side, you are seeing from this side. Okay, it is only a projection that I am putting here. Okay, x versus z. So, it will look like this. You understand, right? It is perpendicular to the plane of your monitor, and then you can get this guy. So, I am only looking at the projection. So, if I am interested in y equals 5 and x equals 7, which means y equal to 5, it is here, and x equal to 7, it is somewhere here. Okay. So, I am just taking, I am putting the plane at y equal to 5, and that is what I get, and then I take x equals 7. So, what will be my final value of the function? It will be a sum of these guys. If I add all these 3 functions, I will get the representative function in space. Agree, right? So, if you go into the specifics of how do you do that, I am just taking, I am fixing y, I am just cutting it. So, you are able to see the cross section, that is how it looks like. For a particular x, I will take the corresponding values, I will add up the z. Similarly, for 3, I will be able to add up those values. Okay. But this is at y equal to 5. If I wanted y equals, I mean I cannot do this here, but I am just saying, if I wanted y equal to 9, I might get a slightly different the way in which it looks like. Yeah, I'll get different these curves, and accordingly at my x it will take different values. Imagine that you have 3 sheets, and then you are going to cut through wherever you want, and the cross sections will vary. You just need to add them. Okay, but you don't need, you will not, this is only for understanding, this is only for visualization purpose. Okay, because this function is nothing but a psi, and it says xi minus x or c, whatever. So, I know the ci, you just tell me where the xi is, I know which basis function I need to take, and then with respect to that center I will estimate what this psi is, that is all. The psi is just some representation, it will be some x cube plus y squared plus something. I will just do that, straightforward. See, this could also just be a subset of the whole problem. Okay, it keeps on increasing also, I do not know.